Today we'll discuss about medicinal chemistry of antihistaminic drug, and we'll also discuss about what is histamine. So let us see this. Yeah. So this topic will cover overview of antihistaminic drugs and overview of histamine and its importance, and also we'll discuss histaminic receptors, antihistaminic drugs, and their SDR. So we'll cover first generation antihistaminic drugs, which includes different classes like ethylene diamine, ethanolamine, propylamine, piperazine, and then tricyclic antihistaminic drugs like phenothiazine and dibenzocyclohexanes, and second generation antihistaminic drugs. We'll discuss why first generation and second generation antihistaminic drugs. So you might have seen these kind of pictures like sneezing, coughing, allergic kind of things. So antihistaminic drugs are drugs that inhibit the effect of histamine. And histamine is related to allergic reaction, gastric acid secretion, regulation of immune responses. So these are the important functions of histamine, mostly allergic reaction and gastric acid secretion. So clinically, they are used for treatment of normal cold and cough disorders, sometimes sedatives, antiemetics, and they are widely available as OTC drugs without prescription. So let's learn about histamine first. So histamine is like meaning tissue or mean histose means tissue. Almost ubiquitously present in animal tissue in certain plants and stinging nettles. So this is your histamine. So if you see carefully, it is made up of two parts. This one. So this is ethylamine and this is imidazole. This is ethylamine and imidazole. So basically imidazole contains two nitrogen. One is this nitrogen and another is this nitrogen. Histamine contains three nitrogen, which is this one, aliphatic, and this is aromatic. So sit carefully. Again, I'll emphasize here that this is your imidazole ring. Imidazole ring contains two nitrogens with one carbon in between, and then this aliphatic chain is connected with around this nitrogen. We'll see how these nitrogens behave in different conditions. So it is synthesized in mast cells, parietal cells, and neurons, sometimes in CNS also. Why this is important? Because it regulates your immune cells, basically allergic reactions. So histamine is one of the many mediators that involve allergic inflammatory responses. Very important. And also gastric acid secretion. Okay. Besides its role in allergic responses, gastric acid secretion of physiological role at axon and several regions in CNS is also been established in the regulation of sleep and walking, endocrine homeostasis, cognition, memory. So this is just not mediator of inflammation, but also for these functions. It also modulates the release of neurotransmitters by H3 receptor. There are other receptors, but we'll discuss on H1 and H2. So how it is synthesized? As already mentioned, that this is your mean, and it is synthesized from histidine. which is amino acid via histidine carboxylic. As you can see here, this carboxylic acid has bond. And this is one of the most important amino acids which I already discussed in our class, uh, like acetylcholine acid, acid or base both. So synthesized locally is not stored and rapidly degraded. So this is the degradation pathway. Two ways, like N-methyl transferase here, N-methyl, and then monoamine oxidase, which we discussed last time also. And it forms carboxylic acid at this. This amine goes out, it forms aldehyde, then acid. Otherwise, diamine oxidase, this is getting hydrolyzed here, and then ribose. This moiety is added here. So this is ribose imidazole acetic acid and N-methyl imidazole acetic acid. You'll find these uh, byproducts in your urine and other places. So synthesizing degradation of histamine. And what is stored and destroyed? In mast cells actually. It is mostly stored and synthesized in mast cells. Mast cells look like this. And it is controlled in IP3 and DAG pathway. So histamine in mast cell histamine is positively charged, held by acidic protein and very negatively charged with intracellular granules. These are the granules. So here they are available. When granules are excreted by excited sodium ions in the extracellular fluid, exchange histamine to these it's free. So it is in exchange with sodium, it is excreted. Histamine is inactive orally because liver degrades all the histamine that is absorbed from the intestine. Because this monoamine oxidase and methylase are available in our intestine, so it degrades. But it is released in presence of any antigen, allergens, or any antibodies. This is how it is being synthesized and stored. So this is where it says PIP3 and IP3 cyclic inositol triphosphate or IP3 DAG, you can say. When this releases your inflammatory mediators, you might have seen this before, where when I shown you the membrane of cell membrane, lipid membrane. So more about the chemistry of histamine. Why I am emphasizing on histamine? Because all your things will be dependent on this compound. So there are three types of nitrogen in histidine, not histamine. So this is alpha, this is pi, and this is tau. Histamine has a pKa value of 5.80 imidazole. This is imidazole. This is ethylamine or aliphatic, and 9.4 pKa of ethylamine chain. So its physiological pH it remains something like this. So this is more or less protonated at 9.4 pKa, and this sometimes gets protonated as we discussed last time how it gets protonated. Acetylcholinesterase, if you remember it. Okay, so this is a pK of 5.8. This is a pK of 9.4. See it carefully again. This is aliphatic amine, so more basic. This is aromatic amine, so very basic. The nomenclature, what it says, in histamine there are three types of alpha, pi, and tau, and their protonation states differ. See, this one is protonated at tau position, and when it automizes, it gets to the pi position. So these will help it in recognition of many compounds and also various types of chemical reactions. So most of the histamine form which is available is this one, because at physiological periods this one exists 96%, only 3% of this 4%. Okay. So other forms of histidine, because this is related to our drug discovery and medicinal chemistry, you must know how and, and how it behaves in biology. So first form is HID, hydrogen at delta position. This is the delta position. Then HIE with hydrogen at epsilon position. This is delta, this is epsilon, this is epsilon, this is delta. And if both are protonated, so this is known as HIP, HID, HIE, and HIP. This nitrogen chemistry plays a very important role here. Let me show you how. So last time we studied medicinal chemistry. I've shown you acetyl polyester, choline antagonists. So you'll get to know what I'm talking about. I think till now it is okay. Um, okay, I'm talking about this portion. So as I mentioned, that imidazole can form a tautomer. So this one I'm talking about. This NH, this N. So once it is acidic and basic, based on that, it will abstract. So this is bipropionated form, as we are studying here. This one, this one. Based on the environment, it can form different tautomers. This one, it will abstract hydrogen, then it will catalyze the acyl polyesterase. Again, it is get deprotonated, protonated. So that's why this is very important. This amino acid becomes very important in many biological areas. Okay, I'll again tell you what is this. So you have this history. Its pK values are different for imidazole and aliphatic. So this aliphatic ring has a pK of 9.4. This imidazole is 8, mostly available as this tautomer form, and it is if when it is protonated at delta position, it is HID. When it is protonated at epsilon position, it is HIE. And when both nitrogens are protonated, it is HIP. Let's talk about stereochemistry of histamine. So results of conformational studies performed on anithistamine and its control indicate both trans and gauche conformation exists. What is this? You have to see this in camera. So this stereochemistry also important many times. Thank you. How does it look like? So meanwhile, I'll share you this PPT portion, which is says different classes of antihistaminic drugs in this one page. This is getting slow. This is what I wanted. So if you see carefully, this is NH3 going up, and this NH3 is going down. So two forms exist, like here. Mostly this form is available because NH is going up, or something like this. So results of confirmation studies performed on histamine and its congeners indicate both trans and gauge conformation exist in solution. So this is trans and this is gauge form. So NH2 is aligned towards this ring. NH2 is aligned opposite to this ring. As you might see here, this is just opposite of alignment. Opposite alignment. We have this alignment. Mostly it will remain as transform because that is more stable. As you might see, it is not getting converted. Just opposite. So, however, transformation of 2-methylhistamine is selective H2 H2 cannot really adopt fully extended transform because of interaction of 4-methyl with the aliphatic carbon chain. This remains as 180 degree and this is 160 degree. So it is not, this is most of it is trans. So what are physiological extents? So cellular mediated of immune and hypersensitivity, anaphylaxis reaction, seasonal allergy, duodenal ulcers, systemic mastocytosis, and gastrinoma, Zollinger Ellison syndrome. We'll discuss it in later slides. It also releases IgE food when it is released actually mediated of IgE food, peanut, milk, sometimes peanut allergies, milk product allergies, grains, strawberries, many types of allergies are there. So you will find it. Drugs like penicillin and sulfonamide, some people are allergic to some drugs. Venoms like fire, ant, snake, bee bites. Foreign proteins like non-human insulins. So these are the mediators of starts release of histamine enzymes. And so non-immune releases like morphine, aspirin, vancomycin, sometimes X-ray, succinyl choline, some anaphylaxis which we don't know, cold and solar urticaria. These are mediators which release histamine. Let's stop it here and we'll discuss